Today we're going to learn about titrations. When we think of titrations, okay, titrations help us determine unknown quantities. Okay, they give us quantitative information about certain substances. It tells us, for example, how pure a substance is, or how acidic a substance is, or how alkaline a substance is, and so on. Right. So, for example, let's say that in this flask, I have a flask over here. Okay, and let's say that I have a 25 cm cube solution. Okay, I have a 25 cm cube solution, and this solution contains ethanoic acid. Okay, this solution contains ethanoic acid, and I don't know the concentration of the ethanoic acid. I want to determine what the concentration of the ethanoic acid is over here. Okay, so the concentration of this ethanoic acid is unknown, right? So here the unknown quantity, or the unknown over here, is the concentration of ethanoic acid, and we can use titrations to help us determine this unknown quantity. Okay, so what we're going to do over here is we're going to use a burette. Okay, we're going to use a burette, right? The graduated burette. Mind my drawing, right? And in this burette I have sodium hydroxide. Okay, I have sodium hydroxide, and I'm going to use a known concentration of sodium hydroxide. So in this case, let's say the concentration of sodium hydroxide is 0.2 moles per decimeter cube. So what I'm going to do here is I'm going to add sodium hydroxide. I'm going to add sodium hydroxide to the ethanoic acid drop by drop. Add sodium hydroxide to the ethanoic acid drop by drop, and I'm going to use an indicator. To tell me about the progress of the reaction. So here what's happening is a reaction between sodium hydroxide and ethanoic acid is taking place, right? Ethanoic acid is CH3, COOH, or you can say CO2H, and it reacts with NaOH, right, to form salt and water, right? So you form CH3, C double bond O minus Na plus and H2O. So here what's happening is, again, the H plus reacts with the OH minus to form water, right? And then you form sodium ethanoate, right? That's your salt. This is your anion, CH3COO minus, and your cation is Na plus. So dynamically are reacting to form salt and water. And now as I add the NaOH drop by drop, right, eventually what happens is that the indicator, I see a slight change in color in the indicator, and that tells me that the reaction is complete. Okay, that tells me that all the ethanoic acid has been neutralized by the sodium hydroxide. And what I realize is that in order to reach the end point, right, in order for the indicator to change color, I had to add 20 cm cube. Of sodium hydroxide aqueous. So for example, if I started with, let's say, 45 cm cube, I figured out that once there were 25 cm cube left, the reaction was complete. The indicator changed color and it told me that the reaction is complete. So I can figure out that 20 cm cube of 0.2 mole per dm cube sodium hydroxide reacted, right, to neutralize the ethanoic acid. Over here I can say that the number of moles of sodium hydroxide that reacted is equal to the concentration times the volume. The concentration of sodium hydroxide is 0.2 and the volume is 20 over 1000. So I have 0.004 moles of sodium hydroxide. So here we know, again, the concentration as well as the volume of sodium hydroxide, right? So that's a known quantity, and using that we can determine the number of moles of sodium hydroxide, and therefore we can determine the number of moles of ethanoic acid that were present in the flask, right? They react in a 1:1 ratio. So I can say that the number of moles of ethanoic acid is also 0.004 moles, right? I have the same number of moles of ethanoic acid, and from that I can determine the concentration of ethanoic acid. The concentration is equal to the number of moles per unit volume, which is equal to, our number of moles here is 0.004 and our volume is 25 centimeter cube. So that's 25 divided by 1000 decimeter cube. So that is 0.025, and this comes out to 0.16 moles per decimeter cube. So that is the concentration of ethanoic acid in this solution here. This over here highlights the use of titrations. Titrations can help us determine information about unknown quantities or unknown solutions. Okay, so here we were able to determine the concentration of this solution, right? Concentration of ethanoic acid in the solution using a known solution. So the question that we have here says, if 29.70 centimeter cube of sulfuric acid of concentration 0.2 moles per dm cube is required for neutralization of 25 cm cube of potassium hydroxide solution, calculate the concentration of potassium hydroxide. The first thing we're going to do over here is we're going to write the equation. So what we have is we have sulfuric acid reacting with potassium hydroxide, which is KOH, to form potassium sulfate, right, K2SO4 and H2O, right, salt and water. This is the neutralization reaction. To balance this, we're going to need two of these because we have two H pluses here, so we need two OH minuses and we're going to form two H2O. Now they've already given us exactly how much sulfuric acid was needed, right? And we want to know the concentration of potassium hydroxide. So the unknown here is the concentration of potassium hydroxide, and we know for sulfuric acid, right, the number of moles is equal to the concentration times the volume, right? So we're going to say concentration over here is 0.2, and the volume is 29.7 centimeter cube. So this comes out to 0.00594 moles of sulfuric acid, right? So this is how many moles we have of sulfuric acid, right? Again, the first thing we're doing is we just find the number of moles of whatever quantity they've given us information about. Then we're going to use ratios to find the moles of potassium hydroxide, right? So we know that for every 1 mole of sulfuric acid, we have 2 moles of potassium hydroxide, right? So if we have 0.00594 moles of this, how many moles do we have? And here if we cross multiply, the number of moles of potassium hydroxide should be twice the number of moles of sulfuric acid, so we get 0.01188 moles of potassium hydroxide. So the last thing we want to do is we want to find the concentration. We have the number of moles of the unknown, right? We know concentration is the number of moles per unit volume, right? Number of moles here is 0.01188 and the volume is 0.025, right? 0.025, that's 25 centimeter cube, right, given to us in decimeter cube. So then that comes out to 0.475 moles per decimeter cube. So that's our answer. That's the concentration of potassium hydroxide. The next question that we have here says that limestone is impure calcium carbonate. 2.00 grams of limestone is put into a beaker and 60 cm cube of 3 mole per dm cube hydrochloric acid is added. They are left to react and then the impurities are filtered off and the solution is made up to a total volume of 100 cm cube. So what we have over here is we have 2 grams of limestone. We have 2 grams of limestone, that is impure calcium carbonate. Okay, we have 2 grams of limestone. And to this 2 grams of limestone, what we do is we add 60 cm cube of 3 mole per dm cube hydrochloric acid. Now this limestone contains calcium carbonate. Okay, it's impure calcium carbonate. Right, so the calcium carbonate reacts with the HCl over here. Right, we have calcium carbonate and limestone that reacts with HCl. And what's the reaction between calcium carbonate and HCl? We know that calcium carbonate is a basic solid, right? And we know that metal carbonates react with HCl to form salt, carbon dioxide, and water. Right? Salt, carbon dioxide, and water. So we have CaCl2 plus CO2 plus H2O. Right? This is the reaction that's taking place here. Now, once they react, right, they were left to react, and then the impurities were filtered off, and the solution was made up to a total volume of 100 cm cube. So what we did was we reacted HCl with limestone, specifically calcium carbonate in the limestone reacted with HCl, right? And then obviously there was some solution that we formed, right, when the reaction. And then what we did was after the reaction, we filtered the leftover solution. Okay, we filtered the leftover solution, and we made it up to a total volume of 100 cm cube. Okay, so what we did was over here, we filtered the leftover solution and then we added water. We added water to make up a 100 cm cube solution. Okay, so this is the leftover solution after the first reaction. Okay, leftover solution हमने लिया and we added water to it and we made it up to a 100 cm cube. Of this solution, 25 cm cube requires 35.5 cm cube of 1 mole per dm cube sodium hydroxide for neutralization. Work out the percentage calcium carbonate in the limestone. Assume that none of the impurities react with hydrochloric acid. So we're assuming that only the calcium carbonate reacts with hydrochloric acid in the limestone. And once the reaction is complete, the resulting solution was made up to 100 cm cube, right? And that 100 cm cube, we took 25 cm cube. We took 25 cm cube from that 100 cm cube and we reacted it with sodium hydroxide, okay? And that reaction was a neutralization reaction. So what do you think was left over after the first reaction that neutralized sodium hydroxide? So here, because we have a neutralization reaction taking place with sodium hydroxide, this tells us that we had acid left over from the first reaction. Okay, because sodium hydroxide is an alkali, right? And alkalis and acids undergo neutralization, right? Neutralization reactions when they react with each other. So here we know that we had HCl left over after the first reaction that was then reacted with sodium hydroxide. So here what we're doing is we're reacting sodium hydroxide with HCl to form sodium chloride and water. Now over here we know exactly how much sodium hydroxide was required for the second reaction with HCl. Right? They've given us the concentration and the volume. So we can say that the number of moles of sodium hydroxide is concentration times volume. Right? The concentration is 1 mole per dm cube and the volume is 35.5 centimeter cube. Right? So the number of moles comes out to 0.0355 moles. And since sodium hydroxide and HCl are reacting in a 1:1 ratio, we know that in this 25 cm cube sample of the leftover solution, we have the same number of moles of HCl. We have 0.0355 moles of HCl. Right? We have 0.0355 moles of HCl. We have the same number of moles of HCl. Now we know that all the excess HCl left over from the first reaction, was made up to 100 cm cube solution. And 25 cm cube of that was reacted with sodium hydroxide. So here we know that in 25 cm cube of this solution we have 0.0355 moles. So how many moles do we have in 100 cm cube? If in 25 cm cube we have 0.0355 moles of HCl, right? How many moles do we have in 100 cm cube? It's the same solution, right? It's the same concentration. We've just taken 1/4 of the solution. So this is just 1/4 the total number of moles of HCl left, right? So here if we cross multiply, we see that number of moles of HCl left is equal to 0.142 moles. Okay? So we had 0.142 moles of HCl left over after the first reaction. Now initially we started off with 60 cm cube of 3 mole per dm cube HCl, right? So that means initially our number of moles of HCl was 60 over 1000, right? That's the volume times the concentration. So that was 0.180 moles. A certain amount reacted in the first reaction and then we had 0.142 moles left over after the first reaction. So we know that this plus this is equal to 0.18. That was the total number of moles of HCl we started with. Right? So therefore the number of moles that reacted here is 0.18 minus 0.142. So that is 0.038 moles of HCl. So 0.038 moles of HCl reacted in the first reaction. So from that we know that for every 2 moles of HCl, we're going to have 1 mole of calcium carbonate, right? Since calcium carbonate and HCl react in a 1:2 ratio, right? So if I have 0.038 moles of this, how many moles of calcium carbonate do I have? I have half as many. So that comes out to 0.019 moles. So here, now that we know the number of moles of calcium carbonate, we can figure out the mass of calcium carbonate that was present in the limestone, right? Because in the first reaction, all the calcium carbonate reacted with the HCl. HCl was used in excess, right? So over here we can say that the mass of calcium carbonate is the number of moles times the molar mass. The number of moles is 0.019 and the molar mass is 100.1, okay, for calcium carbonate. So this comes out to 1.90 grams of calcium carbonate. So we had 1.90 grams of calcium carbonate in the initial 2-gram sample of the limestone. So here, if you want to figure out the percentage purity, right? You want to figure out the percentage purity. The percentage purity is basically the mass of the pure calcium carbonate divided by the total mass of the sample, right? So that is times 100 times 100. So that is 1.90 divided by 2.00 times 100, and that gives you 95.0%. So that is the purity of calcium carbonate in this limestone.